Presumably when you talked about alcohols, you did reduction of ketones and esters, right? Sound familiar? Yes, no, maybe, in another lifetime. Let's try it. If I take a simple case like this, and I want to make the secondary alcohol, how do I do it? Reagents to make that into an alcohol? And a what? We have two different ways of reducing an aldehyde or ketone to an alcohol. One, mild sodium borohydride and ethanol. Did we talk about that before? Okay. Relatively easy to do, relatively mild, however, only works for aldehydes and ketones. Does not react with acids, esters, acid chlorides, amides. Doesn't do some of the things we'd like to do. It's not generic in terms of its ability to take out a carbonyl group. The other possibility is this. Lithium aluminum hydride. Generally, this is the source of most organic chemists' first lab fire. Because you underestimate just how nasty it is if it gets near a drop of water. It's usually used in diethyl ether, so, you know, if something's really nasty, let's put it in something more flammable than gasoline just for fun. It's actually a very good solvent for it, but the point is, you got to be careful handling it. And afterwards, you add very carefully dilute acid to it to protonate the oxygen. In both cases, you're going to end up with the alcohol. Secondary. Okay. So here is a common problem. Simplified. This is a very simple version of a very, very common problem within organic chemistry. And that is competing functional groups. They happen all the time. When I started this course, I told you most of organic chemistry consists of very, very small number of reactions and a large amount of manipulating protecting groups and or reaction order, which we learned in the aromatic chapter. So, how do I do step one? How do I take them both out? Why would you choose that? Is there another option? Within what you've talked about already, is there another option? Within what we've talked about already, is there another option? No. Sodium borohydride does not react with acids, esters, or acid chlorides. It will not take out an ester. So you do not have another option for this. If you want them both gone, you can't be nice to them. You have to use a strong reducing agent. Okay, that takes them both out. How do I take out only the ketone? What? I only want the ketone going, I can use the milder reaction. Notice, no need for protecting group. I just use the reagent that's more chill because I'm going after the functional group that's more reactive. So I just tone down the other portion. If I take up the reducing power, I take them both out. If I take it down a little bit, I'll take out the ketone. Okay. This is the world playing nice with you. Generally, that's not how interesting molecules end up. There is a certain amount of Murphy's Law when it comes to making things. If there's a hard way, that's probably going to be what you get stuck with. So let's say I need the ketone, but not the ester. Now I don't have selective reactivity as a possibility. This is inherently more reactive towards nucleophiles than this is. So there's no way of tweaking the nucleophile that's going to give me an opposite preference there. So what do? I have to take advantage of the fact that it's more reactive, get it to react with something else first to block it. So, in that case, first step, make the acetal. Generally the cyclic version, ethylene glycol, strong acid. That gives me a protected version of the ketone. Then, what? After the first step there, I'm here. I no longer have a ketone. Now what? Now I got to take out the ester. Why would you choose that? Sodium borohydride can't do it, neither can most other reducing agents. I have to use the sledgehammer. Lithium aluminum hydride, followed by dilute acid to protonate. And generally, I would probably isolate that and purify it. Experimentally, that's lab practice you don't have to worry about before I took the acetal off. Because what I'd like to do is make sure there's none of this left in this. So then I would probably go for a separate step, still the same reagent, but it's going to take longer, it's going to require some heat. So I would probably stop in between just for safety's sake, plus I have to get all the metal junk out of there, so I would have to do an extraction. So that would be a separate step, even though it looks the same reagent-wise. I'm actually, in this case, removing lithium and aluminum leftovers. So there is that's why it's written as a separate step. You might be able to get away with doing it all in one, but it's generally not a good idea. So, when we have competing functional groups, we have two possibilities. Well, three, technically. Rarely you want to take them both out. That's not normally what happens. If you want the more reactive one to do something, that's easy. Because you can tone down the reactivity of what you're using on the other portion. It'll go only for the more reactive one. If you want the less reactive of two functional groups, you have to go through protecting group land. There's no other option. You're stuck with it. So you have to know something. The only one you really have to worry about for aldehydes and ketones is the acetal. That's really the only one that's used most of the time. There are very few exceptions. So it presents the larger problem which you'll see in virtually every organic synthesis paper you look up, which is problematic competing reactivity, and you have to work around it. You work around it by shuffling protecting groups in and out of the synthesis. The problem with that is protecting groups cost money. Protecting groups take time and effort to put on and take off. So if you don't have to do it, you'd like to not do it. But if you have to deal with differential reactivity, you really don't have any choice in the matter. You're stuck with it. So learn to love it. Okay, so in terms of strong nucleophiles, those you've seen before, the hydride reagents, Grignard reagents. To a lesser extent, hydroxides, occasionally things like nitriles. The weaker nucleophiles that we're going to deal with, generally we deal with those, we're looking at probably going to another step. Because much like the acetal, we get halfway through, but we're in a medium where using water as a leaving group is still reasonably possible. So we're going to see that happen quite a lot, where we have to protonate to get a nucleophile to come in, and then we end up with a second protonation, water as a leaving group, and a second nucleophilic attack, or an internal second nucleophilic attack. Just so that we actually have this in our brain, to make sure we have it down, we had our hydrides up there. If we're dealing with Grignard reagents, where do they come from? From an alkyl halide. Doesn't have to even be an alkyl. It just has to be a carbon halide. And it specifically has to be one that has no acidic hydrogens. So if I need a nucleophile that's an aromatic ring, I know how to make the bromide. All I have to do is throw a little magnesium in there and give it some time to react, and I have a Grignard reagent. In simple cases, we'll buy them because they're available commercially. Why would you make something if you don't have to? And they're generally cheap. But you can't always rely on that. Sometimes you have to make something a little more complicated because you need functionalization that's not there in the stock version. Okay, what does it do? I put my Grignard reagent around an aldehyde or ketone, what happens? It behaves as if it's an isolated anion. It behaves as if it's a carbon as an anion. So I end up here, I end up here. So I have my new R group. Well, I have the aromatic ring, so let's redraw it. I get my tetrahedral intermediate, rehybridization at the carbon, yada, yada, yada. Afterwards, anytime we use an organometallic, so anytime you see a metal put in place, especially if it has the nucleophile attached to it, afterwards you're going to have to put in something acidic to do protonation. So this is during, afterwards, this is post-reaction. Generally it's aqueous acid, generally very dilute because we don't want to cause problems, and we then get an alcohol. With our new alkyl group attached to it. Okay. What happens if I want to use that? if I want to do a Grignard reaction on that, specifically is what I'm saying. So, pKa is about 9. Why is that a problem? It is, you're right, so don't freak out on me. Let's try it. Let's see if I have methyl magnesium bromide, simplest possible Grignard reagent. This pKa is about 9. So what I'd need to compare it with is the pKa for methane. If that were protonated, I get something which is exceptionally non-acidic. What this means is we cannot get away with strong carbon or hydrogen nucleophiles if there are acidic hydrogens anywhere nearby. That means if we're going to use a Grignard reagent, we're going to use a hydride reagent, there cannot be any OH, NH, or SH anywhere. Can't have it, period. Not only will that react vigorously, it also is generating methane in the presence of probably a lot of heat. We call that a flamethrower. Not generally a desirable lab outcome, unless you work for the Department of Defense. Then you might, get promoted. So, not a good idea. So if we wanted to use this, if we want to do a Grignard reaction on this, what do we have to deal with? Once again, same problem as before. This is a much more reactive functional group than this is. So, I have to get rid of it temporarily. I have to put something on that oxygen instead of that H that I can pull back off later. Otherwise, I'm going to have a reaction that either doesn't work or at least doesn't work well. You might get away with it as long as you're careful about gas evolution, because you might actually be able to get away with this just being deprotonated and just use more of the Grignard reagent. Not exactly good technique, but you might be able to survive it and still get the desired product at the end. Generally speaking, though, if there's an acidic hydrogen around, you've got to take it out before you do anything else, because it's going to screw you up. All right, so that comes into play a lot later. That's why I want to bring it up now. We cannot do strong nucleophiles, alkyl lithiums, alkyl copper reagents, alkyl magnesium reagents, or aryls of any of those, or at least lithium aluminum hydride in the presence of acidic hydrogens. They will react with that much more quickly, and you have nothing to do the actual reaction you wanted done. Okay. So, with some very basics out of the way, let's look at a few of the things we can actually do here. Well, we can get to alcohols. That much we know. If one of those is a hydrogen, we can get to carboxylic acids from oxidation. We can get to acetals. We can also do Grignard stuff to get us to tertiary alcohols. The hydrate really doesn't deserve to be a separate reaction because we don't generally want that, but it is something we have to consider occasionally, so we'll put it up. Doesn't seem like much of a building block list so far. It doesn't seem like it's living up to the hype. But remember, this gives us access to all types of substitutions. This gives us access to all the acid derivatives. The alcohols give us all the alcohol and ether reactions we had talked about. We have a couple of others. We can turn that into an alkene. The exact reverse of an ozonolysis, we can actually make a double bond from this, which is considerably easier way to make alkenes than anything we talk about in part 1. We have a couple of different methods of getting rid of the carbonyl entirely, replacing it with 2 hydrogens. Depending on what's there, we've talked about 2 of them. One of them in the aromatic chapter, one of them today. There's another one that's more common, but it's a long mechanism. We're not going to get it done in the next 10 minutes. We also have access to the imines and from there amines. We can make enamines from that, and then that will come into play in functionalizing what's next door. And we're not even talking about alpha substitution, we're just talking about what we can do with the carbonyl itself. So we can take it up or down in oxidation state, we can turn it into a leaving group, we can turn it into a nitrogen, we can make it into an alkene, a diol, primary, secondary, tertiary alcohols, depending on choice of reagent and starting material. We can protect it if we need it there for later. We have a lot of possible reactions here, but they're going to come down to exactly the same very, very small number of mechanisms. Now, I do not want to start the nitrogen ones today because I don't think I can get one of them done before you're going to be leaving. Those you should look at. Imines and the Wolff-Kishner reduction are very lengthy, but we're going to talk about them tomorrow in some detail. One additional one which does actually have some use, we don't use it that often, but one that is worth putting on the list before we call it a day. And I have to add one additional piece of detail to it so you understand why it's useful, is this. If I can make a nitrile, which you can do with an SN2 reaction from an alkyl halide, if I treat that with acid and heat, I can turn that into a carboxylic acid. So, as it turns out, the cyanide is a nucleophile. The inorganic version of a nitrile will, with some assistance, go after a carbonyl. Now, depending on what reagents you're using, you may be under acid or basic conditions here. Acid condition is a little bit problematic because you're generating hydrogen cyanide. Nice way to die if you do it wrong. But afterwards, if you hydrolyze that, you end up here. An alcohol next to a carboxylic acid. If you have skincare products, you know these. Those are alpha hydroxy acids. Now, the ones in skincare products are naturally occurring for the most part. But this is very similar to the functional group layout of an alpha amino acid. And so a lot of drug candidates will have this layout. So the ability to put that carboxylate in right next to an alcohol comes from yet another version of a nucleophilic attack on an aldehyde or a ketone.